Imagine opening your Cambridge Physics 9702 exam paper. You spot a question on solid-state physics, you write down exactly what you memorized from the textbook, and you still lose the top band marks. Sound familiar? It happens all the time. Today in this explainer, we're completely skipping the fluff. We're going to jump right in and expose the one tiny, yet absolutely devastating mistake that costs students crucial grade boundaries when they're dealing with crystal structures and the coordination number. Think about a standard rote-memorized answer. Honestly, it often looks perfectly fine on the surface, doesn't it? But then compare that to what happens when it meets the dreaded examiner red pen. There is literally an exact 3-second window where a student loses a mark. Why? Well, because while the answer might state the correct technical label, it completely lacks the underlying microscopic reasoning. The student stated a fact, sure, but they totally forgot to explain the actual physics. Section 1. The Flawed Revision Trap. You see, when you're under intense exam pressure, simply regurgitating memorized labels completely crumbles. The central concept that examiners actually want to see is that the macroscopic behavior of a solid can only be interpreted from what happens internally, down at the atomic or carrier level. So that leaves us with a massive question. What is the one hidden examiner clue that changes your answer completely? Stick with me because in just a moment, I'm going to show you the exact clue that transforms a losing answer into a top-band, high-scoring answer. But first, we really need to set up the underlying structural framework. Section 2, the top band 4-step framework. Okay, let's dive into this. If you want to stop bleeding marks on these questions, you've got to abandon scattered facts and adopt this incredibly rigid sequence. Step 1, define the core idea. Step 2, describe the microscopic mechanism. Step 3, identify the measurable consequence. And finally, Step 4, connect that consequence to a real-world application. Moving strictly from concept to evidence to scientific reasoning to the final application, that shows you, examiner, you understand the topic deeply enough to dominate both short and extended exam questions. It's a real game changer. Section 3, mastering the coordination number. A really strong approach to the coordination number shouldn't actually start with some dry definition. Instead, I want you to ask yourself this: what physical effect does this idea help explain inside a solid, and why on earth does that matter for real materials? By starting from a real-world phenomenon and then working backward to the microscopic atomic picture, you're actually building a deep understanding instead of just rote memorizing a bunch of labels. So the crucial point here is unpacking the definition properly. The coordination number in the strict context of solid-state physics refers to the number of nearest neighbor atoms surrounding a central atom in a crystal lattice. But here is my explicit warning to you, stating this formal syllabus definition alone is exactly where most students lose their marks. Trust me on this. The examiner already knows that you know the definition. What they want to know is what physically happens because of it. And this brilliantly illustrates the next steps of our framework: the mechanism, the consequence, and the application. Real materials behave differently because their crystal arrangement, which is dictated by the coordination number, directly controls their packing density, their bonding direction, and their defect tolerance. This microscopic mechanism is the exact thing that determines whether you're looking at fragile semiconductor wafers, incredibly heat-resistant aerospace turbine blades, tough structural alloys, or even brilliantly clear gemstones. You absolutely must connect that microscopic packing to these observable, macro-level consequences. Section 4, the Spot the Error Interactive Challenge. All right, now that you've got the framework down, let's put your examiner hat on for a second. Read the scattered, flawed explanation that a student wrote on their exam paper. The coordination number defines the structure, which is why the aerospace material is stronger and better. Take a really good look at that sentence. Critically analyze it. Let's pause for a second. Where exactly did the student lose the mark? Think back to our 4 steps. They gave a definition. Well, sort of. They gave an application, aerospace materials. But what did they skip entirely? They gave the application without linking it back to the underlying microscopic mechanism. They completely missed the cause in cause and effect. No way an examiner is giving full marks for that. Let's look at the breakdown. A flawed application-only answer just drops a fact, like it makes materials stronger. But the top band, cause and effect answer? That one follows the discipline. It says, the specific coordination number determines the atomic packing density and bonding directionality, so that's the mechanism, which governs the material's defect tolerance. There's your consequence, making it suitable for high-stress applications like aerospace turbine blades. And that is the application. A disciplined paragraph that explicitly connects cause and effect will always score significantly higher than a scattered collection of facts. Section 5. Rapid memory triggers for exam day. To make sure you don't fall into that scattered fact trap when the clock is literally ticking down in the exam hall, I want you to write these 4 rapid memory triggers down right now. Number 1, what is it? 2, what changes inside the solid? 3, what can we observe outside the solid? And 4, where does this actually matter in technology? If you can answer these 4 prompts aloud from memory, you have successfully internalized the required definition, mechanism, consequence, and application. Your revision for this microtopic is entirely secure.
Section 6. The diagnostic cliffhanger.
Okay, so you now know exactly how to structure your answer, from the microscopic level right up to the real-world application. But there is a massive catch. What if you use this perfect framework on the wrong command word? Whether the examiner asks you to explain, describe, evaluate, or calculate dictates the entire mark band. Using the right framework on the wrong command word is actually the hidden cause of lost marks for even the absolute best students. But don't worry, we are going to solve that exact problem. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations.